So welcome back to the final session of our webinar. The next talk is by Brian Biztek from the School of Chemistry at University of Bristol. So please do submit questions. There's going to be a discussion session at the end of the next series of talks when there'll be a chance for the speakers to answer questions. Brian, please do carry on.
Thanks. So this presentation is about aerosol production from singing, speaking, and breathing. It involved a team of aerosol scientists from Bristol, as well as a group of medical doctors and clinical people from different hospital systems, Imperial College and Public Health England. The work was sponsored by the Department for Digital Culture, Media and Sport, and funded by Public Health England, and we acknowledge a number of organizations for the loan of equipment and also the provision of space to conduct these measurements. So motivating this work were a number of clusters of COVID-19 associated with choirs around the world, as Shelley talked about in the previous presentation. And as a result of that, governments instituted some very severe restrictions on singing and on playing woodwind and brass instruments, and that's had some significant cultural, economic, and health impacts. For instance, the closure of performing arts, restrictions on religious and school performances, bans on gathering or limitations on gathering for amateur choirs, and of course lost tax revenue. But fundamentally, what wasn't clear is whether singing was inherently worse than speaking, or whether it was the context associated with singing that seemed to result in a number of these clusters. So for instance, when we're singing, we're often doing that as a group activity. It involves sustained vocalization and often a higher sound volume than when we're speaking. So the work that I'm talking about today has been published as a preprint, so it's not peer reviewed yet, but it's published on ChemArchive, and you can see the details at the bottom of the slide here. So the design of the project involved a cohort of 25 professional musicians, professional singers based largely in the London area. These spanned a range of different genres, including musical theater, choral, opera, and some others. In terms of different vocal parts, we had about an even split among soprano, alto, tenor, and bass, and again, also an even split in terms of gender. And we conducted these measurements in an orthopedic operating room, and the reason that we did that is because it just so happens that the air handling systems in orthopedic operating rooms filter out virtually all the particles. So we have a zero background environment. So as we prompt the singers to perform different activities, we have confidence that what we're measuring is coming directly from them and not from background within the room. So the participants would come into the room and they'd be directed to perform a sequence of activities into a funnel that was connected to an aerodynamic particle sizer, which is an aerosol measurement instrument, and that instrument measures aerosol between about 0.5 micron and 20 micron diameter and provides information like number, concentration of particles, and the size distribution of the aerosol. So just to give a sense of what the protocol was, again, the participants were invited to follow a sequence of events. Each activity was repeated 3 to 5 times to look at consistency. And so we started off by having the speakers singers sing one note in the mid-range of their vocal part at a defined volume, in this case 70 to 80 decibels. We then had them do that again, but at an octave higher. Then we had them speak the happy birthday song on a loop for 20 seconds at 3 different volumes, so 50 to 60 decibels, which is just above a whisper, 70 to 80 decibels, which is about normal speech, and 90 to 100 decibels, which is around the range of shouting. We then had them sing the happy birthday song, again on a loop for about 20 seconds at the same 3 volumes, so we had a comparison for speaking and singing at the same volume. We also investigated their breathing, so we had them breathe in through the nose and out through the mouth, and then also in through the nose and out through the nose. And then at the end, we repeated the initial activity, which was singing a single note in their mid-range for about 10 seconds. And this allows us to compare to what they produced when they initially sang at the very start, to judge to whether there's any drift over time or how reproducible over the course of an hour a certain activity is. So what I'm showing here are box and whisker plots showing number concentrations, and to make this a bit more interpretable to you, I'm plotting number concentrations relative to each participant's emission at while they're speaking at 70 to 80 decibels. So by definition, then the value for speaking at 70 to 80 decibels is equal to 1, and then all these box and whisker plots are all the individual values are relative to that to this value of 1 here. The dots here are all individual participant data, and so the y-axis is the relative number concentration. Each box and whisker plot represents a different activity. And so if we start off by looking at singing the single note, so the very first and the last activity that we examined, what we can see is that they span a similar range in terms of the relative number concentration, the number of particles produced, and also the medians are very similar. They're within 10% of each other. So what that tells us is that there's some reproducibility across the measurement in terms of what people are emitting. The next thing to look at is as we change the volume. So regardless of the vocalization, we see a steep increase in number concentration, and that's on the order of greater than an order of magnitude, on the order of a factor of 13, as we go from the lowest volume to the highest volume. And then if we compare speaking and singing at the same volume level, we see a modest enhancement for singing relative to speaking on the order of 1.5 to 2.5 times more particles produced while singing compared to while speaking. The last thing to point out here is that breathing, this is breathing in through the nose and out through the mouth, that spanned a very wide range, more than 2 orders of magnitude. And breathing, what people emitted while they were breathing really didn't have very much to do with what they emitted while they were speaking or singing. And in fact, 4 participants emitted more while breathing than while speaking at 90 to 100 decibels, the highest volume that we looked at. Okay, so that tells us about the number concentration, but it doesn't say very much about size distribution. And we're interested in size distribution because that can give us information about the mass of aerosol produced. Also, size tells us about how long those aerosol would remain airborne. And they can give us some information about deposition within the respiratory tract. And so we determine the average size distribution for each activity across the whole cohort. So we have speaking at 70 to 80 decibels. In red is singing at 70 to 80 decibels, then speaking at 90 to 100, and singing at 90 to 100. And I show that again in this inset on the top right here. And what we can see is that there's a bimodal distribution here. And so this first mode is associated primarily with breathing, and it's less than 1 micron. The second mode is associated with vocalizing. We call it the laryngeal mode, and that's above a micron. And what we see is that regardless of the type of vocalization, whether it's speaking or singing, we see both of these modes. And they both increase as we increase the volume. There are some interesting details in here that I don't have time to get into, but if you ask me questions about that later, I can talk about that. We compared these size distributions to what's reported in the literature. So this blue line is from Johnson, a paper published in 2011, and we see a very good agreement between our measurements and what's reported in the literature. The last thing I want to point out here is the breathing size distribution. We can see that we see a bit of a bimodal distribution, but the second mode is much less pronounced, and so there's a shift to much smaller sizes. So fundamentally, breathing is different from vocalization, but for vocalization, we see similar size distributions with increasing volume. So from the size distribution, we can then calculate mass concentrations by assuming a density for these particles. And so now I'm showing mass concentrations. Again, we're making this relative to each participant's emission while speaking at the mid-volume level. And so the takeaways here are, first of all, that breathing produces a less mass than speaking or singing. And that's because the size distribution is shifted to smaller sizes. And so in principle, that can reduce some risk if we assume that the dose scales with delivered mass. Again, if we look at, for both vocalizations, the dependency on volume, we see that it's very steep, and we see a 20 to 30 time increase in mass associated with increasing volume. And then if we compare speaking and singing at the same volume level, again, we see some modest increases for speaking relative to singing, and that's on the order of 1.5 to 2.5 times more aerosol produced while singing, sorry. To conclude, what we saw was that aerosol generation is highly sensitive to volume. We're talking about orders of magnitude here. Singing somewhat enhances aerosol generation relative to speaking at the same volume, but we're talking about a factor of 2. Breathing aerosol spans a wide range, but it produces smaller particles, so there's less mass associated with that. I didn't talk too much about this in the presentation, but what we see is that the aerosol production is log normally distributed across the participants, so some people inherently produce much more than others. And so when we're thinking about guidelines and whether it's, speaking is more risky than singing, or singing is more risky than speaking, singing is a bit more risky, but really it's the context that we need to be thinking about. So we need to be thinking about the volume of the vocalization, the number of participants that are involved, what the environment that this activity is taking place in, so what's the ventilation like, and how long this activity will take place. And so with that, I'll finish up. Thank you for your attention.